Okay, so we've been talking about work, we've been talking about power, and now we're getting into the nitty-gritty details of energy. We're going to start with our first form of energy, which is kinetic energy. Okay, and all of this is going to relate back to the same concept that we're talking about, which is work. And if you remember, work is always measured in joules. So, we have, how was this given to us as ninth graders? Well, in ninth grade science, you were given a bunch of different equations, and you probably were told that kinetic energy is the energy of motion, okay? So in other words, it's the motion of the object has a certain amount of energy, and even in chemistry, we started to look at the kinetic molecular theory in terms of there's energy associated with the motion of those particles. So again, we have the mystery machine. Scooby-Doo and the crew are traveling along at some constant velocity, so they have motion. And we know that it has mass, okay? And so then how much kinetic energy does it really have? So again, this is a typical problem that you probably saw in ninth grade science. So again, we're looking at it from our equation here. Kinetic energy is just 1/2 mv squared. The mass was given to us, so I know that the mass was given to me as 2750 kilograms, and I know that the velocity was given to me as well, which is now 25 meters per second, and I'm just going to set it up to figure out my kinetic energy. Okay, so it's just 1/2 the mass, 2750 kilograms, times my velocity, 25 meters per second, quantity squared, and that's how I'm going to figure out my kinetic energy. So I'm just going to grab my calculator quick, and we got 25 squared times 2750 times 1/2, and we get an answer of 859,375 kilograms meters squared over second squared. Oh, hey, a kilogram meter squared per second squared is the same thing as a joule. Because again, if you remember, joules were Newton meters. Newton is a kilogram meter per second squared. So when we take newtons times meters, we get kilograms meters squared per second squared. So this is really saying joules. Okay, that's a lot of joules. Now you do have to remember that joules are really, really small units of energy. Okay, and we probably would talk about this in terms of kilojoules. So you have to be careful and make sure you read your questions, because they may say how many kilojoules is there. And so we could do a conversion here where all we did is convert 1 kilojoule, kilojoule is equal to 1,000 joules. And so if I just took my answer and divided it by 1,000, I'd get how many kilojoules I'd have. All right? So again, this is the basics of what we were learning in ninth grade science. It's the same basics that we're learning here. We have motion, we have energy. All right, moving on. So now, how does this change when we get into a physics classroom? Well, we're never looking at just constant velocity. Apparently, you know, the mystery machine would have to start at rest, and it would have to speed up, and there would have to be something that would take place here. So again, if we see differences in velocity, the only way we can get a difference into velocity is if we have an acceleration. So accelerated motion only happens when we have a net force, okay? And that's kind of our key thing. And that's what we were looking at in the last term, our last unit was we looked at how we got those net forces, okay? And so it's all based on the motion of the particles, or motion in this case of the mystery machine, and it has to go from one velocity to a different velocity. So we're looking at the mystery machine, and it travels through some distance. Hey, that was kind of cool. Let's look at that again. So the mystery machine has a velocity at this point. Okay, it has an initial velocity, and then at the end it has some final velocity. Okay, and so let's just go back here, and so we can say, what's it going to look like? So it has an initial velocity, it has a final velocity, and we have some distance d. Now again, these things you might recognize as things from our kinematics, so the things that we very first started with, okay, are things that we like to do. So in other words, if I know a V, and a D, I should be able to find the A, okay, based on this information. And so I look at the board and I say, which equation am I going to use? And I'm going to use equation number 3. So my final velocity squared is equal to my initial velocity squared plus 2AD. And if I rearrange this and solve for A is nothing more than my final velocity squared minus my initial velocity squared divided by, let's see, 2D. Okay, so in other words, that's what A is equal to. Okay, that's a way to find an acceleration. Well, this acceleration is the same acceleration that we get from our net force. Remember, net force is nothing more than a mass times an acceleration. So this acceleration is the same thing. It's the same thing. So when we start to figure out, well, how much work has been done or how much work has happened here, we can look at work in terms of kind of a force times some distance, right? That's how we equate work, and I call this then net work when I'm talking about net forces. So in other words, our work is nothing more than looking at this acceleration, okay? And so if I look at work, net is now equal to a mass times my acceleration, which I'm going to write now as, VF squared minus VI squared over 2D, that's my acceleration, okay, times D. I can see that mathematically the D's are going to cancel. So the D's disappear, okay? And if I write the divided by 2 as a 1/2, and the M, and then apply it to each part of my VF squared minus VI squared, we can look at this in terms of the amount of work is related back to that kinetic energy. This is great. So the net work done when a net force applied through some distance is nothing more than the change in my two kinetic energies. So in other words, I had kinetic energy when the mystery machine was back here, and I had kinetic energy when the mystery machine was there. And there's kinetic energy there, and there's kinetic energy there, and the difference between those two kinetic energies represents the amount of work that was done to get there, okay? So that's kind of our big ticket right there. So now, net work equals a change in kinetic energy. There's my big equation. My net work is equal to a change in kinetic energy, or what I had on the other slide, okay? The net work is just the work that is applied force through a distance done by less the amount of friction force. So in other words, when we start to look at net work in some problems, we would look at maybe our work from an applied force less our work from, say, a frictional force. Okay, so friction always acts against us. It goes back to our simple machines and why the simple machines were not as efficient. So we lost some of our work or our energy due to friction. Okay. So now here we go. Let's look at a nice little picture. I have a wagon being pulled by this little girl. And so I can see here that the wagon has a mass, okay? And we would maybe say that there's an F of G associated with that wagon, and of course if there's an F of G associated with the wagon, we might also have an F normal, and there's probably a little friction force associated with this, and then she's pulling it with this handle. Now that pull on that handle is that applied force. But that applied force is acting at some angle. So we have a force that is being applied. And so now we can learn some things about this girl in this wagon. Okay? And so maybe we actually can set it up as a little question. So a girl is in a parade. She's pulling a wagon that has a mass of 35 kilograms. The coefficient of friction for the wagon in the road is 0.15. And the handle makes an angle of 20 degrees. So if she pulls with a force of 300 newtons through the distance of 5 meters, then what is her velocity? And this would be her velocity at the end, because we're saying that she's starting, we're going to assume that she's starting from rest. And I should have wrote that in there, but I didn't. So if she starts from rest, then what is her final velocity at the end, okay, from doing all this work? All right. So again, you can see I kind of have my free body diagram already written. So my force applied, and I'm going to switch colors here. Oops. Losing time. Here we go. My applied force would be looking at this right here as well as this right there. So I have two forces that I have to contend with. So this is good practice based on what we were learning from last time. Okay, and so now when I look at my two forces, I know that this one I'm going to call the parallel force because it's parallel, and it's actually now the applied forces and the cosine of my angle. And this one right here, I'm going to call that the force perpendicular, is the applied force times the sine of 20. Okay? And so now I can start to look at how much work was done. So what was my applied work? Okay, my applied work is my force here, cosine 20, times the distance that we're going to move. And the distance there is 5 meters. Minus my frictional work. Now my frictional work deals with a frictional force. My frictional force is going to be, okay, the coefficient of friction times the force normal, but my normal force is going to be my weight minus my force perpendicular. So in other words, my coefficient of friction, 0.15, times my weight, 35 times 9.8, times minus my force applied, sine 20. Okay, so again, I don't have as big a normal force because I'm lifting up a little bit. So this represents the lifting up a little bit. Now the applied force is just a value that I have there. It's 300 newtons, so I would go ahead and plug in 300 newtons in there, plug in 300 newtons there, and then I could solve this, and this would give me my net work. Okay, so my net work is going to be equal to some number. And I'm going to leave it blank, and I'm going to let you do this on your own. But that'll give me some value in joules. Now that's equal to my change in my kinetic energy. Okay? Well, because I start at rest, my initial velocity was 0. So in other words, my joules that I have for my net work is just equal to my 1/2 m, my final velocity, squared. And I know my mass, it's 35, and so now I can actually solve for VF. And I'm just going to do this quick just to give you guys some answers before my time runs out. I've got 30 seconds here. I don't think I'm going to make it. So anyways, I'll try to maybe give you that answer tomorrow. But there you go. That's how we kind of look at this in terms of our net work. Oops, I'll just back up. Okay. So next one, potential energy. Potential energy tomorrow night.